Okay, we have another problem on caches. In this problem, we are asked to assume the CPI is 1 as long as your cache hit rate is 100% and the cache latency is 1 cycle, which is easier in some sense because you don't have to account for data hazard penalties and control hazard penalties. You only need to worry about the remaining cache miss penalties and its impact on CPI. So the CPI equation would be 1 plus instruction cache penalty and data cache penalty. So we are also given that the processor clock frequency is 200 megahertz. It's often useful to think about clock cycle time. So the clock cycle time will be 1 over 200 mega. Mega is again 10 to the power of 6 hertz. So it's 1 over 200 10 to the power of 6 seconds. So that will be 10 to the power of 3. That's 1000 divided by 200 nanoseconds. So that would be 5 nanoseconds. Okay, so we have some information on our hand. So let's go and look at what the problem asks us to do. So it asks us to consider two different changes to the hardware and reason about which one will get higher performance. So to compute that, we are going to compute the CPI of each of these options. So the CPI of option 1 is again going to be 1 plus instruction cache penalty. So in this case, we are asked to double the clock frequency. So doubling the clock frequency is not going to change the fact that you need to access the cache for every cycle, every instruction, because recollect that fetch, decode, execute, mem, write back are the 5 stages that you need to go through for every instruction. So the fetch stage involves accessing the instruction memory. And so for every instruction you access the instruction memory. And for this problem, the instruction cache hit rate is 95%. So which means the penalty would be 1 minus 95%, that is 1.05. And now you need to multiply that with the memory latency. So the memory latency for this option is 40 cycles. So we'll come back to that in a moment. And then for the data cache, we are asked to assume that 30% of instructions are loads and stores. So of the 30% of loads and store instructions, how many of them miss the cache? That depends on the data cache miss rate. That is 100 minus 90, that's 10%. So 10% of all the loads and stores miss the cache and go to memory. And if you go to memory, it's going to cost you 40 cycles. Alright, so you may have noticed an inconsistency here with respect to the main memory latency being 40 cycles. In the previous slide, we said in the baseline it is only 20 cycles. So why is it the case that when you double the clock frequency of the processor, the main memory latency increases to 40 cycles? The answer is the main memory latency doesn't really increase. It stays a constant in terms of the actual time it takes to access the main memory, right? So what changed is the time of the clock period. So when I say that the main memory latency is 20 cycles and the processor clock frequency is 200 megahertz, then the main memory latency is really 100 nanoseconds. Right? Now that does not change when I double the clock frequency of the processor. So now when I double the clock frequency of the processor in option 1, now my main memory latency is still 100 nanoseconds, but now my clock frequency has gone up, and so my clock frequency has doubled. So when my clock frequency doubles, my clock period would reduce by half. So before it was 5 nanoseconds, so now it would be 2.5 nanoseconds. So this would give me 40 cycles for main memory latency. Okay. All right, so now let's compute the CPI for the option 2. So again, it's going to be 1 plus for every instruction I have to incur the I have to access the instruction cache. So in option 2, I'm going to double the size of my caches. So when I double the size, the cache hit rate goes up. So instead of 5% miss rate, now it's only 2%. Now the main memory latency is the old main memory latency because the frequency of option 2 is same as your baseline. So it's 20 cycles. And then I have still 30% of instruction cell loads and stores. And the miss rate has gone down because I doubled my cache size. So it's gone down to 5%, and the main memory latency is the old main memory latency, so that's 20. So now if I do the math, it will be 4.2 and 1.7. So you will see that the option 2 is clearly worse than option 1 in terms of CPI. But when you're reasoning about performance, CPI is only part of the equation. What really matters is the execution time of a program, and that depends on CPI, but also you need to multiply that CPI with the number of instructions that you're going to execute, right? Because CPI is clocks per instruction. So if you have to multiply by number of instructions, you'll get the total number of clock cycles. But that again doesn't tell you the whole story because it's just expressed in terms of the clock cycles. What we want is time. So for that you need to multiply this with clock cycle time. Now let's see what that is for option 1. So for option 1, the CPI is computed as 4.2. We don't really know the number of instructions because we don't really have any program to reason about this. So I'm just going to assume it's n. And the clock time, like we said, has actually gone down for option 1 because the whole point of option 1 is to double the clock frequency of the processor. So it went down to 2.5 nanoseconds. For option 2, you'll have much better CPI. Instruction doesn't change, but the clock cycle time, however, is the baseline processor's frequency, which is 5 nanoseconds. So now if you do the math, this comes to 10.5 times n. This comes down to 8.5 times n. So you will notice that option 2 is still the better option, but now we can confidently say that option 2 is better, but not as good as it was before, because 4.2 is almost 3 times that of option 2, but the performance difference is much more tighter than what we originally thought it would be. And the reason for that is the benefit of option 1 is expressed in terms of the clock cycle time, whereas the benefit of option 2 is expressed in terms of the CPI, because we were able to reduce the CPI by increasing the cache hit rate.